simplest form, single particle analysis involves relatively few steps. So we start by importing the movies, and the movies, for instance, in this example, there will be data coming from this Empire dataset that is an apoferritin. It has a 0.49 angstrom per pixel. This is the pixel size, and this is the movie size with 50 frames within each movie. So we have 30 movies of this kind. We will see later all the details of the data, but just to go with an overview of the whole pipeline. So you import the movies, you align those movies to produce micrographs. So now we have micrographs, and then you estimate what is the contrast transfer function of the microscope, basically what is the defocus of each one of the micrographs. You choose your particles, here 5,000 particles, then you extract them and classify them to get rid of bad stuff. Then we, for instance, this is apoferritin, but we will see that some of the particles still have some iron inside, so we choose the ones without iron. Then you construct an initial model if you don't have one already, and then you refine these particles that are 3600 with respect to this volume to produce a final structure. So let's go over the different details. So first of all, we have movies. So if we have movies, you double click in any one of them, and then you are able to see the raw data. So we will see how data is collected in the microscope. So if it comes, is it coming? Yeah, so it takes some time, and so let us see how the data looks like. So this is the XMIP viewer. Normally it is not so slow. Yeah, it has opened twice. So here what we can see is enhanced contrast, so that probably it is better, this one, brightness and contrast, so that we can see that there are values that go from 0 to 3. So we see that most of the values are, so it is 0, 1, 2, 3. We see it in here in this histogram. So this is the raw data collected by the microscope. Has opened a few times. Okay, so from this data, where we can barely see anything, we first align the frames, so just to see an idea of how things look like. So you take your input movies and you will align all of them, and at this point we will make a reduction by a factor 2 just for this example, but not necessarily in all projects, so it depends on what is your goal. And then there are some other parameters that we will not use here. So typically the most common action within Scipion is just to change the input of the different protocols. We call every one of these boxes, we call them a protocol, and then you change the input to adapt to the previous calculations, and the default parameters are typically fine, and if you know what you are doing, you can change them. And yeah, after aligning, this is what we see. So now we have the micrographs, that align micrographs, and the trajectories. So we see that from frame 1 to frame 2, it moved this much. These axes are pixels, these are pixels. The pixel size here was 0.5 angstroms. So it moved this many pixels, and then from frame 2 to 3, 3 to 4, and so on up to frame 50. So we see kind of global trajectory. There are also local movements that are not summarized here. And then after aligning all those micrographs and averaging, what we see are the apoferritin particles in our micrographs. Okay, so next step is to estimate the power spectrum, the CTF of the microscope. So let us see. So here is the calculation done by CTF Find 4. So we see the power spectrum, the experimental power spectrum, and two representations of the predicted power spectrum. And also we see here the trajectory, what is the defocus, the defocus ratio. So in principle it should be 1, because we wouldn't like to have astigmatism in our micrographs. We have resolution, that is an estimate of up to which frequency this prediction and these observations agree, and then the fitting quality and the micrographs. And you can make all kind of plots. So for instance, you can make histograms of resolution if you want. So if you can, this is the resolution estimated from the CTF. So you see some micrographs have a very low resolution. Probably that is a mistake of the fitting. So we can sort by this, go to the end, and that's right. There was a mistake in this estimation of the CTF of the defoci, and that resulted in a loss of so the resolution estimate was really bad, but it was because of this mistake. And this is already points out to something that we will reinforce during the course. That is the idea that all algorithms, no matter how good they are, they will make mistakes, and these mistakes propagate throughout the analysis. So if you don't pay attention to them, you will all the particles coming from these micrographs will be incorrectly corrected for the CTF, and these errors will get into the structure. Depending on what is the fraction of the errors, these number of errors can be catastrophically affecting your structure, or maybe just some small nuisance. Okay, so in this very simple analysis, we are not correcting for this kind of stuff. So we let everything go. You can also make plots, or I don't know, if you want, you can sort by something, and then we have sorted by the defocus ratio, so we can make a plot of this one, and then we see that it goes from 1% to almost 10%. And what is a correct astigmatism level of astigmatism cannot be calculated here, can be done with XMIP, for instance. We will see it along the course. And yeah, so you can explore your results in quite various ways. Then you pick your particles, and for instance in Criollo you don't have to give much, so there are some models that are generally good for most of the projects, and if you don't give the box size, it will be automatically estimated. It has been estimated to be 119, and now we can see, for instance, if you double click, you can see the set of coordinates. I don't know if I did it right. Let me do it again. Okay, so here we can explore the particles, and again there are mistakes. So we can see that some of them are not correctly chosen. This is not a particle, this is not a particle, these are not particles. There are missed particles here. So again, the same idea. Algorithms, they all make mistakes, no matter how sophisticated they are. And for instance, here you can see that some of the particles are going to the carbon edge. But in this very simple processing, we let everything go, so we don't correct for these mistakes, and then you extract your particles, and here what we have is a cropped version of all those particles. It is a very tight box, and again, along the course we will see what is the effect of the box size on the reconstructed structure. But in this example, we have used this box. We can see some of them, we can see the iron. Some others, we can see that it is in the middle of the particle. So the particle is not in the middle of the box, but the box is covering half and half of a particle, of two particles. So yeah, so this is how our data looks like. Now we classify into 50 classes, and what we see is that there are many good things, and then there are crappy images, and then we see the ones with the iron, and we see also, this is an interesting idea, that the alignment of all these images, these 200 images, you can see the images here. So the alignment of all these 200 images, it has been driven by the particle itself, but the alignment of this one has been driven by the iron. So that is why here you see the internal structure of the particle, while here you see an overall shape, but you don't see details inside the structure. Okay, so now we can take the particles we like. So let's say that we like these particles, this we don't, this we do, and yeah, you choose all of them. And once you have chosen them, so let's say these are all of them, I don't know if that is true or not, then you can create a subset of particles, or you can create a subset of classes. So instead of having 50 classes, the difference between a class, a set of classes, a set of averages, and a set of particles is that the set of classes is these representatives along with the particles behind. So we have seen that for every class, that for instance here there are 35 images behind this class. So the classes are representatives plus the particles behind. The averages are simply the representatives, and the particles are simply the particles of all these particles, of all these classes. So if we create a subset of these classes, we have 3600 particles. Okay, so I did that already. So here we have the particles without iron, so these are particles, and then you go into an initial model, and this is the initial the estimate of the initial model resolution is 400 angstrom resolution, and we can see that it looks like a correct structure. It has some features that along the course we will see that we don't like. So for instance, this is kind of artifactual, these shadows inside, and we will see what are the causes of this kind of stuff. And then we use a different program. This time we use CryoSpark, where before we use Reliant for that, and we use CryoSpark to do the final refinement of this structure. And then here we have pretty good structure. We can see it in 3D. It is generally it is important to have a look at both levels, so 3D, but also at the level of slices, to see if we detect any pattern that shouldn't be there. And we see some nice stuff. So for instance, here we see alpha helices, and yeah, so in general it looks good, and it was a very fast processing, very simple steps, and we are done with a structure that nominally it has a resolution of 2.7 angstroms. So, and this was done with very few particles. So we will see along the course many modifications along this structure, this pipeline. So this is the simplest pipeline, and it has all the steps necessary, but not the ones to produce the very best results. Okay, so just a reminder, so you import your movies, you align them, you estimate the focus, you identify your particles, extract them as small patches, then you classify, choose the classes that you want and the particles coming from those classes, then you construct an initial model, and you reconstruct. This would be mostly it. See you in the next project.